Hello and welcome to lecture 5. Today we will be concerned with the PID control and lead lag design. And today I'm not in the VS Code environment, instead I'm in this Pluto.jl notebook. So this notebook format is very similar to Jupyter that you might be familiar with since before. But the distinct difference is that Pluto is reactive. So as soon as you change any cell, all other cells that depend on that cell will be recomputed automatically. Let's get into it. So I start by loading some packages. Control systems base, the plotting package. Pluto UI provides some interactive sliders that we can use to tune controllers, and the robust and optimal control package. The model we'll consider today is given here on zero pole gain format. So it has one stable pole and it has one unstable pole mirrored in the imaginary axis. It has a gain here. We can see the pole zero map here, that we have the two poles mirrored. So this is an unstable system. Since we have a unstable pole here, we know that there is a fundamental limitation. So there is a rule of thumb that says that the gain crossover frequency should ideally be more than 2 times the frequency of this unstable pole for the closed loop system to be reasonably robust. So that's something we'll bring with us when we do the design. Then just to set the stage here, I have a frequency vector that I will be using to plot frequency responses. And then I've created a little helper plot here, a PID margin plot. It creates one margin plot, and then it draws a vertical line at this fundamental limitation here. So this pole is located at roughly 4.85. So this 2 times that would be the fundamental limitation. It sets some limits, and then it draws a Nyquist plot as well, and packages those 2 plots together into one plot. So that function will be used later. So the first step is to do PID tuning. And to do that in a nice way, I've set up a number of sliders here. You can see the sliders here. And that's quite easy to do. I just say I have a slider KP. It's a slider. Here are the range of values the slider takes. I want to show the value. So it's shown here, and the default value here. And then I create 4 of those. But to show them in a very nice way, I can minimize that cell. I create a markdown string. And this double backtick creates kind of a LaTeX math symbol. So this looks like a math K. And then I call the bind macro from Pluto UI. And bind says that the variable k will be bound to the value of this slider. And this $sign is just to interpolate this slider into the markdown string. And the result is that I get a nice LaTeX k and then the slider. If I had just displayed the slider like this, I would see the slider, but I wouldn't see any description of it. All right, so let's hide that. And then I create a PID controller using the values from this slider. So we have the gain, proportional gain, the time constant for the integration, the derivative time, and the filter time constant for a second order low pass filter. We can look at the documentation here. So if I place the cursor over the PID function, we get documentation here. So right now this is just a transfer function, and we can activate this cell here below. Let's see, where do I do that? Okay. So now we see if I drag these sliders, the plots here will be adjusted automatically. So here we see a margin plot. This is a Bode plot of the open loop system. So P times C, the loop transfer function. And we see if I increase the gain, the gain increases in this plot here. So what I will do first is I will try to increase the gain such that we meet this fundamental limitation of the gain crossover frequency as a start. So something like that maybe. And we see that the phase is constant here, negative 180. So maybe I'll try to add some derivative action to lift the phase here. And I can do that, and we see now indeed we start to, this is a Nyquist plot, we start to move away from the critical point when I increase the derivative action. And we also see that I lift the phase here. But we know that if we add derivative action, we should always add some filtering as well, so I will do that. And when I add the filtering, we see that the Bode curve will bend down for high frequencies, and we see that we start losing phase here again. And if I add a lot, we will also see it in the Nyquist plot. It starts curving in towards the critical point here. All right, so I don't want to add too much filtering because then I will lose phase here again. So we add maybe something like that. And then to increase the low frequency gain here, I add integral action as well. And this is the time constant. So if I make the time constant large, we have a small amount of integral action. And we see now the Nyquist curve will bend up and go towards infinity here because we have integral action. And the gain curve will increase here. So if we see if I add too much integral action, then suddenly I will start dropping in phase margin. So we see the phase margin here. It's currently around 50 degrees. If I add more, I will drop, and then suddenly it would become unstable. So maybe I add something. I now look at this curve, and if I move this here, we see we will start to affect the phase at the gain crossover frequency. I don't want to do that, so somewhere here was okay, I guess. Then I can play with the derivative gain so that I see that I have a decent phase margin, and now I have 60 degrees, and that's plenty of phase margin. So right now we are happy with this design, but of course we are not done yet. We have only looked at the loop transfer function here. So we should always ask ourselves, is the system stable? And it is. So here I calculated the closed loop transfer function, and I asked if that's stable, and it is. We can also simulate this. So here we form the closed loop system from a reference to the output. I perform a step response, and I plot that, and we see that it looks okay. But I should not only look at the output, I should of course also look at some internal signals. So for instance, I might be interested in looking at what's the input signal when I perform this step. And I can do that. I will do that by calling extended gang of 4, like that. And if we look at the documentation string for extended gang of 4, it will give us this system. So it will give us the transfer function from W1 and W2 to Z1 and Z2. But I'm not interested in the load disturbance response here. So I'm only interested in the transfer function from the first input. So I will access this function like that from the first input. And now we see two plots here. I should change the Y label to phi error and U. All right, because the extended gang of 4 function does not give us the output. It gives us the control error here. So rather than the output, we now see the error between the reference and the output. And here we see the control signal, Z2 in the bottom. And we see that for this step response here, we get a huge spike in the control signal, and that's not perhaps desirable. So we should do something about that. And one thing we could do is to apply a filter on the reference signal. That's usually a good idea. Another thing we can do is to not send steps on the reference and instead send something like a ramp, perhaps. So we can do that. So we can call the LSIM function instead of the step function. And then if we provide a function as a second argument here, it's a function of x and t. And if we just output 1, that would be the same step as before. So if we compute that, it should, when it's done, give the same result, and it does. But we can change this to a ramp, and the ramp takes this form. So this is now a function that outputs t until t becomes 1, and then it just outputs the minimum value then between 1 and t, which is 1. So that would be a little ramp, and if we look at that, it takes a while to simulate it. We now see that we have a much more gentle control signal. So that looks quite nice. If we want to add also a reference filter, we could do that. We could multiply here by a transfer function. Something like that perhaps. And we will get an even smoother response. Yeah. All right. So now we have looked at the time domain simulation. We should also look at all the transfer functions involved in the gang of 4. And I have prepared that here. So here I create a gang of 4 plot, and I plot a line corresponding to a maximum sensitivity value. So that's this green line here. And I also plot a line corresponding to a maximum complementary sensitivity function value. That's this line here. And I also plot those two circles corresponding to the same value in the Nyquist plot. So we see here that our design stays below this maximum value, so that's an indication that we have a reasonably robust system. And we see that we have some high frequency roll-off here in the transfer function from measurement noise to control signal. So that's indeed quite desirable. Otherwise our controller would be using a lot of high frequency input signal, and that might damage our system. So with this we are quite happy with the PID design. And in this case we tuned the PID controller manually using these sliders here. And we set the PI and D values ourselves. But we can do this also in a different way, and I call that automatic loop shaping. And for the automatic loop shaping, I will create 4 new sliders, and we will go into what those mean after we have looked at this plot here. So here we see more or less the same plot as before. But in this case, we will not set the gain values for the PID controller. Instead, we have one slider that controls the maximum allowed value of the complementary sensitivity function. So we see as I drag that value, the circle here in the Nyquist plot changes radius and center. And we see that this horizontal dashed line here also changes. So we immediately control the peak value of this function. The other slider here is an angle. And we see when I drag that, we will change this angle here. So that's the point where the open loop Nyquist curve is tangent to the circle here. So we can choose that. We have an omega slider that controls the frequency here at which this tangent point is where the Nyquist curve hits the circle. So we see that will correspond roughly to the bandwidth of our system, and then we have the same filtered time constant as above. And we see if I drag that, I will affect the high frequency roll-off in this plot here. So I can maybe I have some requirements on the complementary sensitivity function. If that's the case, then I can immediately set those here. And otherwise these are just tuning parameters essentially. So maybe I tune it something like this, and I keep an eye on the maximum sensitivity here, we see that indeed I have maybe a high peak in the sensitivity function here. I could reduce that perhaps by filtering less. But if I filter less, then I instead have higher derivative action here, and maybe that's also undesirable. So this is obviously a trade-off. But I can play around with these values and see how the Nyquist plot and the gang of 4 changes here. All right, and here at this particular design point, I got a warning saying that the calculated Ki is negative, so this would be the integral gain. So that's perhaps undesirable, and we can see the gains I have calculated here, and indeed it's negative here. So maybe I need to drag this slider up a bit. That didn't work. All right, that worked. All right, so maybe I'm happy there. And we see that the controller I got out of this is a fairly high gain. K here is 41. And when we tuned it ourselves up here, we set K to 25 in this case. So that's an indication that maybe this controller is quite aggressive. And we could perform the same evaluation of the simulating in the time domain for this system as well if we wanted to. But that was it for PID tuning. And now we will have a look at lead lag design. So lead and lag design is kind of a classical control design technique where you start with a basic controller and then you add elements called lag links and lead links. So a lag link or a phase retarding link, it lifts the gain for low frequencies, but it also makes the phase drop. So it's a trade-off there. And the lead link is the opposite. It increases the gain for high frequencies and also lifts the phase. So that's usually desirable, but it also comes with noise amplification drawbacks. So here I start with a PID-controller, just a transfer function of a constant gain here. And I might set that to approximately meet my fundamental limitation. And then after that, maybe I would like to shape the loop here to add low frequency gain. So I can do that using a lag link. And if I look at the docs, the lag link has 2 parameters, A and M. And it says there is a rule of thumb that says that if A is a 1/10 of the crossover frequency, then we will have at maximum 6 degrees of phase margin loss. And we know that the crossover frequency should be at least this fundamental limitation frequency, and that's roughly 10. So if I set the frequency to 0.1 times 10, I follow the rule of thumb. And the next argument, M here, is the gain at low frequencies. So maybe we'll set something like 10. And we see now that I did indeed lift the gain here, so that looks good. And the phase did drop. And we see I have now a phase margin of -6, which corresponds to the rule of thumb here. But we see that the system here is in fact not stable, right? Because the Nyquist curve goes on the wrong side of the critical point. So I need to add also a lead link to add some a phase advancing link to lift the phase here around the gain crossover frequency. And there are 2 functions. One is called lead link. I find that a bit difficult to use. The other one is called lead link at, and at here stands for at a particular frequency. So here I choose the frequency I want to have the peak of the phase curve on, and I choose how much I want to lift the gain. So I know I want to lift the peak at around the gain crossover frequency 10, so I write that immediately, and I want to lift the gain by a factor of 10 roughly, and the base gain K will just be 1 in this case. And if I do that, we see indeed I did lift the phase curve around here, and the peak now occurs somewhere just above the fundamental limitation frequency here. And now it's starting to look quite good here. I have a phase margin of 44 degrees. I have a gain margin here. This is for a gain reduction, so I can reduce the gain by between a factor of 4 and 5 and still be stable. So now I have this transfer function here is my current controller. Maybe I'm actually a bit aggressive here because we see the gain crossover frequency is well above the fundamental frequency here. So maybe I can reduce that to reduce the gain here slightly. Maybe something like that. We see now I'm close to meeting the fundamental limitation here. But we see that I have as many numerator coefficients as I have denominator coefficients here. So this transfer function is proper, but not strictly proper. So I should probably add some high frequency roll-off also. I can add a low pass filter here. And I recall from before that this was a good time constant. And if I add that, we see that now I did drop a bit in phase. My phase margin before it was 50 degrees, and now it's 43 degrees. And we see that the loop transfer function here bends down much faster, but maybe that's an acceptable trade-off to get some low pass filtering. So I can activate this gang of 4 plot as well, so we can inspect the full result. And we see that compared to the PID controller I tuned before, I now have a slightly higher peak in the sensitivity function and also a slightly higher peak in the complementary sensitivity function. And indeed, we see the Nyquist curve goes inside of these circles here. And so I could spend some time further tuning the lead and lag links here if I wanted to. But since I have already come up with a PID controller that I consider better, maybe I will be happy with that. So here is the PID controller. We see that it uses quite a lot of high frequency gain here. The amplification here is close to 1000, whereas the lead link here is significantly less high frequency gain. So if I want to make this curve stay out of this sensitivity circle here, maybe I will reduce the filtering slightly. If I change it, the time constant to half, we will see that now it moves further outside of this circle. So maybe that's acceptable. All right, as a last check, we check if this closed loop system is stable. So here is my lead lag controller, and indeed it is stable. And then I am happy. So I wanted to mention that the documentation for the stuff we have been covering today is in the control systems documentation under design. You will find a lot of the design examples here. And you will also find some documentation strings under synthesis. So here we have the functions. We can look at lead link act. We see the documentation here. We also have an example called control design for a pendulum on a cart. This is in the robust and optimal control documentation. And here I do many of the things that I did in the tutorial today. So I do this manual loop shaping with the PID controller and so on. And today we use the Pluto notebook, so pluto.jl, and we created these sliders here for tuning. If you want to work in VS Code or you want to work in a Jupyter notebook, you can use a package called interact.jl that also provides this kind of interactive sliders that work in Jupyter notebooks. All right, thank you for today.